Good morning, Honorable Committee. My name is Preedee. I'm come from Konkan University Demonstration School, and I am here to present my research of self-study siphon for the IYPT 2026 competition. This is problem description that the important word is specific shape that this siphon, unlike a standard siphon that must be primed by filling the tube, if only requires dipping. The standard siphon needs starting force to make a difference of pressure. Once water pass the crease, a continuous water column is established. The geometry of the tube has section that can accelerate water in BC section, which water falls and gains velocity due to gravity. First, we use HL as head loss, and over the short startup interval, acceleration is constant. We can calculate net force from difference of drive force from difference of pressure of inlet and outlet, and the loss force that can write as low AGHL. Then using Newton's second law, and we have formula of distance that water move through, which relate to time. Using quadratic formula, and then we got a formula of T and HL. Another variable is angle, which we measure experimentally through V0 and T. We calculate the initial velocity by using principle of conservation of energy. Let's move to the experiment. I said two experiments. One is relation between V0 and T, and two is relation between theta and T. Before experiment, we need to find the K constant of the rubber band that we use in the experiment to find the velocity. Using normal first equation, and we can calculate K by measuring all parameters substituted in the equation, and we got the value of K, which are 80.12 and 15.02 kilogram per second per square seconds. After knowing the K constant, then find the velocity by using earlier formula. This value of each initial velocity range from 286 to 575 centimeters per second. This is experiment 1 and experiment 2 setup, which has siphon and setting board. At the top, stress rubber band and foundation built by bricks at the bottom, and a tank full with colored water. Observing in experiment 1, we observing T for 3 times per each velocity and calculate HL. As V0 increase, time T first decrease, then increase again. There's an optimal for minimum time, and the loss height increase with V0 at first, then decrease when V0 become too high. In experiment 2, the relation between theta and T to examine how the tube's bending angle affects the flow time and the loss of height, while keeping all other conditions identical to the previous experiment. So the T and HL is relative to theta. Time T is minimum value at the theta 60 degrees, and the calculated heat loss nearly constant across all angles. To summarize all the experiment, the fastest time T at 1.08 seconds is at velocity at 528.75 centimeters per second. This maximum speed confirming the unnecessary trade-off between speed and the energy efficiency, and the angle effects of theta is less significant. YT was minimized at 60 degrees, but the HL remained nearly constant regardless of the angles. This is the conclusions. Thank you for your attention.